Swayam Prabha. Digital India. Educated India.
Let's continue with constraint. I have to speed up a bit, but initially I want it to be little slow so that we are all on the same page. You see the motivation of why we're doing all this. And now again, because it's a kind of crash course, so many things I want to talk about. You are not going to get details of everything, but don't worry, you can look into the literature and the slides a bit more. But I mentioned to you about the book, so you can get more information, not only this book but other optimization books as well. I'm just trying to give you as a first course to you to know overall what is in this literature, what are possibilities and things like that. I think the best thing to do is, if you always think of in the context of a problem that you have, either is your thesis problem or some other problem in your area, and think of an optimization problem which should be design or some setting up, like that first slide I showed you with different problems, and then think of the variables, objective function, constraints, and what I am doing here, how that will be applied there. If you think with the context of a problem, you will enjoy it a bit more and you can see what the relationships are, and then you can ask me an appropriate question. Alright, so I'm thinking of a design or decision set of variables x1 to xn, there are n variables. And I've already talked to you about this NLP, objective function to be minimized, constraints, inequality, equality, there could be number of them, variable bounds. Okay, so we talked about that. Now when you have constraints, so far the bounding phase golden section for single variable, the combination of both, and either Nelder-made direct search method or the gradient based methods ending up with marquards. And there are many other sophisticated methods like conjugate direction, conjugate gradient, reduced methods. There are so many different methods. Frank-Wolf. My first book talks about many of those algorithms actually. We didn't talk about constraints at all. Now we're talking about constraints, and constraints are important in real world problems, which means so far you only had F, there is no G and H. But when you have constraints, there is a theory, and the theory says if any x that you have satisfy all of these conditions, in addition to there are some constraint qualification conditions, we are not talking about it here, but they usually comes with gradients again. Once you do that, that's called a KKT point. KKT comes from the three authors, Karush, Kuhn and Takar. These are the three people who came up with this theory. And so if your solution X satisfies all of these conditions along with that constraint qualification conditions, it's called a KKT point. Okay, that doesn't mean they're optimum, but an optimum has to be a KKT point. So it's a necessary condition for an optimum to satisfy these conditions. Now of course, as you see, to satisfy these conditions you need to know the gradient of every objective function and every constraint function. If you don't have them, you can't apply it. Okay. Once you satisfy this for the particular, so x is given here, x is coming from your algorithm and you are checking if it's a KKT point. If it's not a KKT point, it's not an optima for sure. If it's a KKT point, it need not be an optima. There requires second order conditions to be checked, but at least it's a candidate, and many algorithms just tries to verify if this is a KKT point or not. So when you solve this, you also find these u's and v's. These are called Lagrange multipliers. Okay, these Lagrange multipliers are called shadow prices. So this is uj, for example. B, so for example, if you have gjx, one of the constraint less than, so let's say I'm going to do less than equal to 0, then if I do it like gjx less than equal to 1, I increase this by 1. Okay, so I'm investigating if I increase my right hand side from 0 to 1 or by unit distance or by delta b, if I increase it by delta bj for the jth constraint, what will be the change in my optimal function value? So this could be my cost and g could be my, let's say, volume constraint. So let's say I'm designing a can with volume inside, I want certain V. So V to be greater than equal to, let's say, 300 milliliter. So, and I minimize the total surface area. I'm two variables, D and height H. Okay. So I can find an F star. I can find the area, let's say A star. That's the optimum for this problem. Now I'm checking, what if I told him 301? So I want a bit more volume, 1 unit of more volume. How will this increase? Because this is going to increase, right? How will this increase? One thing I could do, I can re-optimize with 300 being 301 and re-optimize and find new A star and then see. But if you know the Lagrange multiplier for this constant, that means U, if you know, this U is nothing but the change in the function value divided by the change in the right hand side. So change in right hand side I already put 1. So U will be basically same as the change in the function value. So you see, doing another optimization, not doing another optimization, if you know these Lagrange multipliers which are called shadow prices, you can actually do some sensitivity analysis. How sensitive is my optimum with the right hand side resource that I put in? It's a very important concept, and lot of design, I'm dealing with a lot of design engineers from auto industries. These are the questions they ask all the time. They're never happy with the design. They give you a project, you did everything and you optimized and given them a result. You think they will be jumping around with that? No. They are looking at it as they are doubting everything. They said, what if I told you that this constraint I can relax a bit? We are basically talking about this. Can you tell us how the solution improves or doesn't improve or what happens? So they are trying to basically do a exploration of the design to see the sensitivities of various parts. These are very important for designers, right? And all these are possible with some of these concepts. Again, I'm not going into the details of it, but this is a byproduct that if you are in case solving these KKTs to check if it's an optimum, as a byproduct is you get the Lagrange multipliers, which tells you the sensitivity part. Okay, now let's talk about an algorithm. A very simple constraint handling algorithm is called the penalty function approach, where what you do is you have the objective function, you add a term, penalty term. This penalty is depending on how much constraint you have violated. So let's take an example. Let's say this f is my original objective function, this line. Okay, going this way. This is my objective function. Where is the minima? Somewhere here, right? I mean, this is the one. So here is the minima. But I have a constraint here that says only this part is feasible, left part is not. So this cannot be a minima. I cannot, because this violates the constraint. So where does the minima go now? Right here. This is my minimum function value, right? So how do this algorithm work? This is how it works. You add the penalty. So with the penalty, one thing could be this omega function can be just this. It's called the bracket operator penalty, or it could be a linear function that says as you are going away from the penalty boundary, the boundary of the constraint, your penalty increases monotonically. It could be a straight line or it could be a quadratic function, whatever it is. Then what you do, so this function is added to the original function with a constant r. So let's say we start with r equal to 0, which means this is not added. I have the original function, p is equal to f, and I minimize using this unconstrained minimization, steepest descent or Nelder-Mead or whatever. So I get this point. Now I change r equal to 1. So this is added to this function, and this function is 0 here, right? The penalty function is 0 here. There is no penalty here. These are feasible. So this is only added to this in this part, left part. So this is my function now. And then this is not added anything. So now this function, where does the minima go? You see here. So I start from the previous point and I solve the new function with this one added with r equal to 1, and I get this point. I move only this much. Then I make r equal to 2 and I make it this function. Minima moves here. So I go from here to there. This is my initial point now for this optimization, and I find that. Then I increase to 3. This is how I keep increasing r, and my minima keeps approaching the constraint minima. So at the end, you are going to be so close here to this minima that you can say, okay, I'm happy with this, and every time you are adding r, you're increasing R, it's not giving me a very different value, so I stop. This is the sequential application of unconstrained algorithm to solve constraint problems. I have a 2 variable example. So here is the constraint. This is the unconstrained minima. When you put R equal to 0, this is where you're going to go. And then you add the constraint and put R equal to 0.1. You see your contour function now, your optima is moved there from here to there. So when you optimize, you get this point. Then increase R to 1, and this is your function. From here, your optima moves here now. And then go to R equal to 10, your optima moves very close to where the actual thing is. So you see, starting from here, you are actually moving this way to the minima. So in multiple unconstrained optimization, you move. This is a very simple algorithm. This one has lots of problems. If you have single constraint, it works nicely. If you have more than one constraint, all these additions that you are doing, they create their own local minima, and you can get stuck into those things. Plus it's a local method, so there are a lot of issues with this. But if you have a single constraint, no matter how non-linear it is, you can try this method. There is a better one called augmented Lagrangian. Very few algorithms have that, but this has a proof that at the end what you get is a KKT point. So nice, right? But the mapping is so complex, I'm not even showing it here. It'll take the whole page to update that function that I showed you here. It's very ugly, but there's a lot of theory behind it, and it basically distorts. It keeps the same kind of topology, but it moves the function. Its optima towards the new optima. It distorts the function. Not distorts, basically relocates the minima that way. Here it is distorting the function. You see the contours between these two, even with the 0.1 change, and then you see how it's changing. The contours change here a lot, which means the objective function is twisted a lot for the penalty function, but for these cases it's not twisted that much. That's why the algorithm works nicely here, but the function is very ugly. And also at the end, the advantage is you get the Lagrange multipliers. So this is by far, I would say, the recommended one, but unfortunately because of the complexities of the function, not many codes have got them. Okay, yeah. Some highlights on the theory on this is that if you have a convex function like this, I tell my students that if a function can hold water, it's a convex function, right? Because there could be one or multiple minima there, but then that's a convex function. And if your feasible space is also convex, this is not a convex function. The definition of convex is if you take any 2 points joined by a line, if all points fall inside that region, it's a convex function. So circles, any regular polygons, these are all convex, right? So ellipse also. So if we have a convex feasible space and convex objective function, then KKT point is guaranteed to be minima. But if it's like this, a KKT point is not guaranteed to be a minima. You need to check the second order. So you see how nice it becomes. You don't need to check second order derivatives. So that's why the mathematicians like to work with convex functions, because there are a lot of theory they could do. I already mentioned this, so let's change that. I'm going to skip this one. This is more into theory, duality theory and all this. So now talking about the exercise that you'll have to do, F-min search, MATLAB, you'll have some experience doing it. This can do unconstrained search, unconstrained optimization. All you need to do is provide the function and a starting point x0, and options allow you to do several things. You want to display iteration wise results or not, plot something or not. All these you can put under options, and then it gives you the solution x, and also the function value there. So it just minimizes the function with respect to x. I think I have an example here. This is a function with 4 optima, as you see, equal optima. I start with this point here, middle point, and the algorithm decided to go that way and give me this minima. If I do slightly over here, maybe it will go this way and give me that, you know. So it depends on where you are starting, how close it is to the current local minima, and you're going to get different answers. Okay, so that's the F-min search result. You see how this goes. And it uses Naylor and Mead search, and it's showing the best point of every iteration. Then MATLAB also has constraint optimization, which is called fmin_con. That was fmin search, and this is function minimization with constraints. So it can handle minimizing the function f. F can be any nonlinear function but continuous. C are the inequality constraints. C equal are the equality constraints, as you see. In less than equal to form, you have to put your constraint function in this form, and some linear constraints. Ax equal to less than equal to b means all your constraints are linear to x. So if you have some linear constraints, you can supply a and b. And this is linear equality constraints, and then you can provide lower bound, upper bound. These are all in vector form, right? So you could actually get a lot of things output from this fmin_con, but these are all the inputs you have to give. Your function, objective function, your x0 starting point, your A matrix, your B vector, your equality A matrix and equality B vector, lower bound, upper bound, and constraint function, the nonlinear ones, the C and CEQ will come here, and then options for choosing an algorithm. There are 4 or 5 algorithms you can choose one from, and then some other plotting features and everything. Okay. Here is the same problem. I put 2 constraints, as you see here. This is the feasible region, this whole part, and one time I started from here. You see how it goes into the feasible region and then goes to the minima. Another time I get that point, it decides to go that way. I thought it was going here, but then something happened, some kind of conditions in the algorithm, and then it comes this way and converges here. Because these are infeasible, so it needs to go to feasible, but for some reason it did not go directly that way. Okay, so it depends on the functions, as I said. Now that these things are so nonlinear, even if you started slightly here, maybe it could have found a shortcut. So it's all in the conditions of how the algorithm is designed. So if you want to change these algorithms to customize it, it's very, very difficult. Okay, because so many things are going on at the background. So these are not very flexible, but you see they work nicely, right? Now these are both equal optima. Which one it goes, you have no control. Unless you know that here I know there is a minima, so if you supply any point here, then you can get there, or that one. Otherwise, if you have no idea where the minima is, it's going to take you there, but which one, you don't know.
Sir,
Yeah,
just
question.
a couple of questions.
Yeah,
When you're talking about, I do understand the optimal solution.
yeah.
But how are we getting this feasible solution space?
By defining the constraints. So you define this constraint boundary that this side is feasible. So there is a mathematical definition of this function. Maybe I'll show you an example, and this is another constraint that says left side is feasible, and then combination of this makes this part feasible, and there are variable bounds that x1 goes between -5 and 5, and this one goes from this to this, and that's how the whole thing is bounded.
Yes. Yeah. If it's like something like linear programming, like if it's an linear inequality conditions, I do understand.
Yeah.
But how do we do it in case of an
So-
transcendental equation like sin x, whatever?
Right, all you have to do is supply it here in this nonlinear. Let me see if I have an example here. No, I don't have. Going all the way to the end, no, I don't have. Okay, I need to show it from my, so when I get into the assignment stage, I will show you an example, where to put these constraints and how this algorithm then takes care of that. Okay, that's a good question. Any other? Okay. Very short about linear and integer programming is that when you have everything linear, all your objective function and constraints are linear, this is what you get. Your feasible space will be bounded by straight lines or linear hyperplanes, because everything is linear. All these constraints are linear functions of x1, x2, right? So this makes this part feasible. Now your optimum, okay, so tell me one thing now. So this is, the blue region is the feasible part, and my objective function is also linear, right? Okay, which means if I draw the contour, it's going to be these parallel lines. The slope of this depends on the respective coefficients of x1, x2 and the objective function. Can one of the point inside this space be optimum, be minimum? Why not? Go ahead, try. That's the correct answer, but why not? Why can't I have this point as a minima? Or any point inside the interior of this blue region? That's because these contour functions will either reduce this way or reduce that way depending on the coefficient values, right? So let's say it reduces this way, or let's say reduces this way, let's say reduces. So that means this one may be 100, this one may be 90, 80, 70, this is and I'm minimizing the function. So I will end up to the last one before I leave my blue region. So maybe there is a line that's going through this one here, parallel to this. That's the last line, and this could be 70, 60, maybe 55. If I want to go less than 55, my line is going to be not intersecting with the blue region. So that's the minimum f that I can get, which is 55. If it's here, it's going to be around 92 or 80 to 88 or something. So it's not minimum. So when you have everything linear, you have a polygon in case of two variables. That's the feasible region, which is always convex. And since your objective function is also linear, it has to be one of the endpoints or the apexes or the entire line. If this function is parallel to this line, then any of these points will have the same optimal value. So you can never have any point inside as your optimal point. Does that make sense? So if I know that I have a polygonal space which is feasible, inside I'll never have the minima, what's the point of searching inside? So there are smart people. There's a guy called Danzig, long time ago, I think it's in 65 or so. He came up with a method that only searches exterior these points. Not even these points. It searches only the corner points. Okay, because you know that one of the corner points has to be the minima. So he has a very fast algorithm on going through the corner points and very quickly figuring out which is the minima, because there will be very few corner points, right? Okay, there is an Indian even smarter guy called Karmarkar. You may have heard. He was an IIT Mumbai student, then ended up joined in US. So he came up with an idea that says when you have many variables, number of variables here is 2, and linear programming can solve 1 million to 10 million very easily because it's a very fast algorithm. But he showed that when you have going over million variables and you have like to the tune of hundreds of thousands of constraints, now you think of a very large dimensional space with lots of these hyperplanes making lots of corner points. Number of corner points also is very large. So Danzig's method, going from one corner point to the next, to the next, to the next, also takes a lot of time. And it takes so much time that he said it's better to search from inside and get to the corner. Because you see how the paradigm shift happens with large dimensions. So he came up with a predictor corrector method, which is now very well known. He got lots of prizes, and I think at some point he got tired with US, and then he came back, and somewhere around Pune or somewhere he settled. He's now advisor to Tata and every other some government places. Genius guy. So he came up with this method which is for large variables, linear programming. His method is known as Karmarkar's algorithm. Okay, so that's the story on the linear programming, but I'm not going again details of how do you find all this. Any standard operations research book will have them. There are a lot of codes available. MATLAB has linprog, which you could do. This brings us to discrete linear programming or integer linear programming. So you have a linear programming, everything is linear, but your variables, some of the variables or all variables are now discrete or integers, which means the Karmarkar's method or Danzig's method will not work because you jump from one to the other, right? So, so these points fall here, but this is not one of the, so here is one discrete, next one allowed is here. So these corner points, if you search, they are always infeasible or mostly infeasible. You have to jump, you have to kind of get to these one of the feasible points which are discrete. So their method will not work. So they come up with this fix up called branch and bound or branch and cut method. What you do is you assume they are not discrete or integers. You assume they are all continuous. So you can use Danzig's method or Karmarkar's method. and you solve them, you find the values, variable values. So that's assuming it's not discrete. Now let's say this problem both have to be integers. That's one of the restrictions. X1 has to be how many trucks, X2 has to be how many buses. So you cannot have 7.31 buses and 4.56 trucks, right? So it has to be an integer. So you say, okay, none of them I can use now, but I've got some good solution. And then you say, I can choose any one of them. Let's say this is my most important variable. I'm going to split this into two numbers, which is the floor and the ceil of the allowable thing. So floor of this is 4 and ceil of this is 5. I'm going to add to this LP1 this constraint and make LP2, linear programming 2. And I'm going to add this constraints to LP1 and make LP3. Okay, I've just added a constraint to each one of them. I can still use Danzig's method and solve again, and I find another solution of x1, x2. I find another solution of x1, x2. Now three things can happen. One, when I add this constraint, it contradicts and I don't find any feasible solution, because inside this LP1 I have a constraint that says x1 has to be less than 4, and this constraint says x1 has to be greater than 5. So obviously there is no feasible solution because they are too contradictory. So you spend a lot of time, ultimately algorithm doesn't give you anything. So there is no point splitting or branching from here. So you say stop this one. Come this one, maybe this one made x1 equal to 4 but x2 9.35. I'm just giving a number, which means x1 is okay but x2 is not. So I still need to work on it. So I again branching it, so x1, sorry, let's say 5.35. So I again take the floor of x2 and ceil of x2, add two more constraints each and call this LP4, LP5, and I solve them. I get an integer solution. I get, let's say, x1 equal to 3 and x2 equal to let's say 5. So I get an integer solution. This is acceptable to me. So I don't want to branch anymore. Okay. Let's say now I come here, I get another thing not satisfy, a branch again, and I come here, I get another integer solution. No, so this gets integer solution, I stop. But this one, let's say I get a non-integer solution. But let's say here the function value is 10 and I'm minimizing. Here the function value I get is 12. So first way to branch is I have infeasibility, so there's no point to branch. Second of bounding. First way of bounding is that I got an infeasible solution, no point for me to branch anymore. Second way is I've got an integer solution, so why do I branch again? I stop. Third one I'm talking about, so I've got a non-integer solution, I'm supposed to branch, but I've already got a feasible integer solution with a function value 10 and I'm minimizing. Here I get a non-integer solution, which means I'm going to branch further, I'm supposed to branch further, but my function value here is 12. Is there a point branching? Why not? Because every time I branch, which means I'm splitting my whole space into two parts, and for the entire part my best value is 12. If I branch, can I get anything better than 12? So imagine here is my space here. This space, feasible space is here. I have the original space there. I have branch. Now this branching is only taking care of this part. I have decided to split it. So this is for my LP6 and this is for my LP7, and this is the inside part that I have not included between 4 and 5, right here. So overall I have got the best solution maybe somewhere here with a function value 12. This is best overall in this. If I split this, can I get anything better than 12, anything less than 12? No, in that case I would have gotten it here itself, because this 12 is for the considering the entire thing. I have split this into two parts, actually three parts. One is there is no feasible solution. So I am not expecting to get anything here better than 12, and I already have a solution with 10. So why do I care? Branching again, so I stop. So these are the three ways you can stop, you can fathom. They call it fathom also. And then you see, you may have an integer solution here, you may have an integer solution here, and then you see which one is better. Now, if you have few variables, this branching takes very less time, and it's a nice algorithm. But I'll show you an example where we had very large number of variables, like 2,000 variables. This doesn't work. It's not a polynomial time algorithm. It's an exponential time algorithm, which means if you double the number of variables, let's say 10 variable version took you 1 minute to get the result. If you double it, 20 variables, it will take more than 2 times of 1 minute. It might take 10 minutes. So time exponentially increases as you linearly increase your number of variables. So when you go to 2,000 variables, it's way too high for the algorithm to work. But it's still an algorithm which IBM Simplex is making a lot of money. Grubby, there are lots of softwares with this method. They are happy with this. I needed that problem for a industry problem, and 50,000 to 100,000 was the range of variables, and I could not use these commercial software. So there is a conference on operations research in US. It's called Informs. Every year about 4,000 to 5,000 people come, and there are all these displays of companies with softwares come. IBM and Gurobi, all of them come. So I went to them with this problem. I told them that I cannot use it more than 1,800 variables. I need to go to 50,000 a year. They look at me and said, "Are you sure?" I said, "Yes, here is the problem formulation." And they try to talk me around on other things. I said, "No, can your algorithm solve this problem?" And they said, "We have to check with our research team." I said, "Please do. I'll give you the code, my problem formulation." After a month, they came back and says, "No, it's too big a problem." They have some versions of it which I have to pay like a whole lot to get it, and I don't know even what. So that's kind of a difficult. So dimensions, optimization literature, in many places you will find they write there is always scarce of dimensionality. As the dimensions increase, the apparent algorithm that works for few dimensions stop working, and I have seen that so many times. So customization is a big deal in optimization. You cannot avoid it. A lot of people don't like me when I say this, but I am being very practical and I am solving. I'll show you some examples. I will show you an example which nobody has solved. I think there are 1 or 2 I have seen since I've done this. A billion variable, not 2 variable, a billion with a B. We could solve using these kinds of problems using evolutionary methods. So there are certain issues with optimization literature and people are working on it, but customization, if you do, then you can solve problems with large dimensions as well.